Okay, we're going to start the last set of notes for chapter 5, and it's called Finding the Area Between Two Functions. So we have been, in chapter 5, we've been finding area under a curve. And when we say under a curve, we really mean under that curve, that function, but also bound by the x-axis. This section, it's not going to necessarily include the x-axis as a boundary. It's going to be bound by two functions. So what does that mean? Well, like I said, thinking back to what we were doing before, I'd give you a curve. So I'm just going to do a really basic example. Like give you the curve y equals 7. I would say, okay, find the area under that curve from, let's do boundaries 0 to 3. Okay, so, you'd go over 3 and you'd say, okay, well, that's just a rectangle. I can find that without calculus. That is this rectangle right here. That's 3 by 7. The area is 21. Well, we're going to change things now. And instead of being bound by the x-axis down here and that curve, we're going to be bound by another line. So I'm going to say, find the area between the curves, bounded by the curves, y equals 7, and let's do y equals 2. So now it's still a rectangle, but I want to do the same x values, boundaries 0 to 3. I want to find the area between these two curves with these x boundaries. So that would be, I'm going to mark this in red, that would be this rectangle right here, not going all the way down to the x-axis. Okay, well, that area still has a base of 3. And now, though, its height is not all the way to the x-axis, so it's 7 minus 2. So right here, this would be 7 minus 2, which is 5. So 3 by 5, that's an area of 15. Okay, that's how you do it geometrically with area. How do we do this without geometry, with calculus? Well, we started off by finding the area under the curve 7. 7 then times the width, dx, from 0 to 3. And we talked about how that would be 21. But I need to then, if I'm going to find the red area, I actually have to subtract. I haven't drawn this yet. I'm going to take the green area, which is this right here, and I'm going to subtract actually this blue area. If I subtract this blue area from the green, you're left with the red. Okay, so that looks like this with calculus. So minus the area from 0 to 3 under the curve 2. Okay, so using calculus, the antiderivative of a constant, you just add an x. So this would be 7x from 0 to 3. And this would be 2x from 0 to 3. And then we use the fundamental theorem of calculus. So this is technically 7 times 3 minus 7 times 0 minus brackets 2 times 3 minus 2 times 0. Okay, so that ends up being 21 minus 6. 21 here minus 6, because the others are 0, and 21 minus 6 is 15, just like we got on the last slide. Okay, so we talked about how to do it with area. We talked about how to do it with calculus. Let's generalize this. So basically, when you're doing this, you're going to take the area of whatever curve is on top and subtract from it whatever curve is on the bottom. Okay, so we did it in two separate integrals back here, But we could have combined this. This could have just been, since they have the same boundaries, 0 to 3 of 7 minus 2 dx. It could have just been that, okay? And that's because they have the same limits of integration. Okay, so that's how I'm going to generalize it. I'm going to generalize it within one integral. So whatever the limits of integration will probably be spelled out in the individual problem. And we're going to talk more about those, but this isn't super mathematical, but basically it's going to be the top function, whichever function is up higher, minus the bottom function. Okay, this is just the big idea, dx. But I do want to talk more about those boundaries. Okay, I have this right here. What are those boundaries? So they can be a few different things. They could be spelled out in the problem. They could say, like I did on this first problem, I said, okay, I want you to do that from 0 to 3. They could say that. And when they say that, basically that means your boundaries are an x equals line. From x equals 0 to x equals 3. Those are two vertical lines. So I actually want to write that down. So what are your boundaries? 1, they could be x equals something like, we'll just do A, which is a vertical line. Okay, or probably even more often, it's going to be where the functions intersect. Okay, and you're going to see that here. Let's actually try this. Let's try this with an example where it's not all horizontal lines. Okay, so example 1. Find the area enclosed by the curves. That's what the directions look like. So notice this problem doesn't say like from 0 to 5. There's no brackets that say that. That's because you really need to know what this looks like. So I'm going to give you a moment before I show you what the graph looks like. You graph this. Take a moment, pause my video, graph y equals the square root of x, y equals 1, y equals negative x plus 6. Okay, it should look like this. Yes? You've got your horizontal line, you've got your square root, and a line with a negative slope. Okay, so what does it mean to have bounded area? Well, looking at this, you know, having dealt with this a lot, I have an easy time noticing what the area is that we're talking about. But that's something that may take some time for you. Now, the area that we're going to actually find has to be enclosed by all three functions listed. So, like for example, I don't know if any of your eyes are going here to this area. That's not what we're talking about. That area is only enclosed by the square root in the horizontal line. So we don't want that area. We want this area right here, all of this enclosed by all three regions. That's what we're trying to find the area of, okay? So back to the big idea, this whole top function minus bottom function, this actually proposes a problem in this one. So we are going to be going from, so our area that we're finding is going to go from 1 all the way over to 5. Okay, so we're going from 1 to 5 is our x values. However, as I move my way to the right from 1 to 5, it's going to be the green function on top over the black function. Okay, green over black. But it's not like that the whole time. It's only green over black, green over black, green over black, green over black until 4. And then at 4, it's red over black, red over black, red over black. So my point is that the top function switches. It's not always the same one. So this means we're going to have to split up. We're going to have to split up our our antiderivatives. So from 1 to 4, it was green over black. So I'm going to start by writing one integral from 1 to 4. And now I'm going to do top function minus bottom function. From 1 to 4, the top function is always the square root of x. And the bottom function is always y equals 1. Okay, so these are the y equals functions. This is y equals the square root of x minus y equals 1. Top function minus bottom function. But that's only from 1 to 4 where they intersect. Okay, so I'm going to evaluate that. And when I do that, that's going to give me the area in between these functions all the way up to there and stop. Okay, so that means I have to add, in order to get the rest of the area, from 4 to 5, I have to add, top function is the line, minus bottom function is the other line, dx. Okay, so that will add to my area the rest of it that I need. Okay, so these two together will give me my answer. And it is a lot of, this is going to be a little bit of work because we have to take the antiderivative of each of these, but neither of them are hard, right? That would be negative x plus 5. Okay, so let's start working through this. The antiderivative of the square root of x, the antiderivative of the square root of x, that's add a power, divide by that power. Adding a power would be x to the 3/2. Okay, divide by 3/2 is the same thing as multiplying by 2/3. And then minus, what's the antiderivative of 1? X. And that has to be evaluated from 1 to 4. So there's just a lot of computation with this. Okay, so then plus, the antiderivative of negative x is negative x squared over 2 plus the antiderivative of 5, 5x. And that has to be evaluated from 4 to 5. Okay, so now we plug in. Okay, so it would be, move over here, 2/3. See if I can fit this on one line. So 2/3 times 4 to the 3/2 minus 4. Okay, so I just plugged 4 in to each of those x's. Then I have to subtract from that. I'm just starting to evaluate this piece. I haven't even touched over here yet. Plugging in 4 and then minus. Now I have to plug 1 in to each of those, and I'm putting it in parentheses because it is a binomial. 2/3 times 1 to the 3/2 minus 1. Okay, so that is just evaluating the antiderivative from 1 to 4. Okay, so then I have to add to that. So this plus sign that I'm about to write is this plus sign up here. Plus negative 5 squared, and the negative is not being squared, remember, so it's that negative, it's like negative 1 times x squared. So negative, and then the 5 squared over 2 plus 5 times 5. Okay, and then that's just evaluating the 5. Now I have to subtract and plug in the 4, so minus parenthesis, negative 4 squared over 2 plus 5 times 4. Okay, go ahead and pause, plug that into your calculator and see what you get. Okay, you should get 13 over 6. That's what you should be getting as you plug that into your calculator. Now, you're going to probably be upset to find out that there's actually an easier way to do this. However, it's not how you probably prefer to think. Okay, so what do I mean by that? Well, same problem without splitting it up, without splitting it into two antiderivatives. So what I mean by that is we're going to totally change which variable we integrate with respect to, which you didn't even know was possible until now. We're going to integrate, instead of integrating with respect to x, we're going to integrate with respect to y. So that means that our change, our width of all of our little rectangles are now little dy's. It's like they're turned on its side. Integrate with respect to y. Okay, so I'm going to take this, and for a moment, I'm going to turn it, maybe. I'm going to turn this on its side. Struggling. Okay, there we go. Okay, so I'm going to turn this on its side, and I want you to go back to that whole thinking of top curve minus bottom curve idea. Okay, so top curve minus bottom curve. If I do it like this, okay, the top curve is always the same. Okay, it's always, you know, as you look and move left to right, it's always the same curve. Okay, it's always this one that is on top. Okay, it's always the same, so there's no need to split it up. So I kind of want to generalize this whole integrating with respect to y. So when we integrate with respect to x, I talked about how it's top curve minus bottom curve. When we integrate with respect to y in general, it's going to be right curve, whichever one is the rightmost. Yikes, I'm still getting used to this, guys. Right curve minus left curve dy. So if we're integrating with respect to y, that also means that our limits of integration have to be with respect to y as well. So basically then, instead of looking at the leftmost x value to the rightmost x value, those are how we thought about our limits of integration last time. Now it's going to be bottom y value to high y value. So low y value to high y value. Okay, so let's try this. So our y values, since we don't have to split it up, let's start with our limits of integration. So we get to go, so we're thinking our limits of integration, our y values, we're going from the y value 1 right here to the y value 2. I'm going to go from 1 to 2. Those are our y values that our bounded area stretches from. The x values that it stretches from are 1 to 5. But now we're in terms of y. So the y values it stretches from is 1 to 2. Okay, so then the rightmost curve would be, let's see, the red line. So that's negative x plus 6. And then minus the left curve, which is the square root of x. dy. So I hope you're looking at this and you're thinking, okay, there's something wrong with this because we're integrating with respect to y, yet we have x's in here. Okay, these are y values, this is a y value, but we have x's in the function That's not okay. We have to fix this. We have to actually write our functions in terms of y to be able to do this. So what would the line y equals, let's see, what would the line y equals negative x plus 6 be in terms of y? Well, subtract 6 and then change the sign. So negative plus plus. X is equal to negative y plus 6. So I actually need to write this in, I need to write that in terms of y. So instead of writing negative x plus 6 right here, I'm going to go ahead and write 6 minus y. So I'm going from 1 to 2. I've got 6 minus y minus, and then what does y equals the square root of x look like if I want it to be in terms of y? So I square both sides. X is equal to y squared. So minus y squared. Now I am ready to integrate. Okay, I'm ready to actually take the antiderivative. Everything about my antiderivative is in terms of y. So this would be 6y minus y squared over 2 minus y cubed over 3. And that has to be evaluated from 1 to 2. So you got to plug 2 into everything and then subtract, and then plug 1 into everything and subtract that from the answer you get when you plug in 2. So you should get the same answer as we got earlier, but you only have to do this process, the fundamental theorem of calculus, capital F of B minus capital F of A. You only have to do that once, whereas back here, we wrote that out once, twice, and we just had a lot of plugging in to do. Okay, I'd much rather only have to plug something like that in just once. So you should get that 13 over 6 again. I do have some more examples I want to do. I'll do those in another video here.